Assalamualaikum and good day to everyone. Now we move to the new subtopic under the chapter 8, which is the third objective, which is to describe the kinematic of a particle that has curvilinear motion along the path but resolve into rectilinear motion along the x and y axis. So it means that we are going to have the rectangular component. So here, 8.3, curvilinear motion. So now, what is the curvilinear motion? So, based on this figure, you may refer to this figure, which is that we have a particle. This is the particle. So, the particle moving along a curved path. So, this is the curved path. So we call it a curvilinear motion. So since the motion is often three-dimensional, so vectors are usually used to describe the motion. So here we have the vector r. So vector r here is the position. So this is the initial origin is from the 0. So the position of the particle at any instant is designed by the vector r with time. So both the magnitude and direction of r may vary with time. So here, let's say if you want to determine the displacement, so displacement symbol is delta. So if you want to get what is the displacement, this delta r, so you need to get what is the vector r prime, because we already established the r, right? So delta r is equal to r prime minus vector r. This one like this. Okay. Alright. So next. So what is the velocity? So velocity represents the rate of change in the position of particle. So here you may refer to this figure. So here we have vector r. Okay, for the position for this particle. And then you must remember that the velocity must be tangent to the parts. Okay, this is part. So this is the part. This is the part. So this is the velocity. So must remember velocity must be tangent to the motion. Alright. So here, the average velocity is given by delta r over delta t, which is the change of time here. Delta t increment or decrease. Alright. So here, the instantaneous velocity is the time derivative of position. So if you want to get the velocity, instantaneous velocity, so you can derive the dr over dt if you know what is the r. Okay, and then the velocity vector is always tangent to the path, as what I mentioned before. So you must remember, if you want to sketch, so you must remember that velocity vector is always tangent to the path. Okay. And then next, acceleration. So here acceleration represent the rate of change in the velocity of a particle. So you may refer to this figure. So you have a change in the velocity for the first time. Here you have v, and then you change to v prime. So we need to get what is the delta v. So what is the delta v? So here, if a particle velocity changed from v to v prime over a time increment delta t, the average acceleration during that increment is equal to delta v divided by delta t. So how to get the delta v? So of course v prime minus v, like this, divided by delta t. Or the instantaneous acceleration is the time derivative of velocity. So if you get what is the v, so you can get the acceleration, because you can derive dv over dt. Or also, if you have vector r, you can have double derivative d square r divided by d2 square. Okay, and then you may refer to this figure. So this figure to tell that the acceleration is hodograph. Okay, hodograph to the velocity. Just now, velocity is tangent to the motion. So now, a plot of the locus of point defined by the arrowhead of the velocity vector is called hodograph. So the acceleration vector is tangent to the hodograph. but not in general tangent to the part of function. So this is photograph. So this is the velocity. So this is the acceleration. So if you want to sketch in the part, so this is the velocity. So this is this is the particle. This is velocity. This is the acceleration. Alright. Next, rectangular component. So what is the rectangular component? So you may refer to this figure. So it is often convenient to describe the motion of a particle in terms of X, Y and Z rectangular component. So we have to fix frame of reference. So this is a position vector R. So this is the curvilinear. This is the part, the motion part. So the position of particle can be defined by at any distance by the position vector R. So if we have the axis X, Y, Z, so here this is the R. So R is defined by the XR plus YJ plus ZK. So here the X, Y, Z components may all be functions of time. So how to determine the magnitude of the position R? As usual, if we have determined what is the X, Y and Z, so we need to square root it. So as usual, X square plus Y square plus Z square. Okay, and then the direction of R is defined by the unit vector. As usual, as in the static. During we study in static. Okay, understand? Okay, here. First, velocity. So now, when we determine the R, so the velocity vector is time derivative of position vector. So it means that after we determine the R, so we can get the velocity because velocity is the derivative of the R. So velocity means that V is equal to dr over dt. So it is equal to this one. Okay, each of the component dx over dt plus dy over dt plus dz over dt. Okay, understand? Okay, now since the unit vector I, j, k are constant in magnitude and direction, so this equation can be reduced to this. So if you want to get the velocity, so we can have the vxi plus vyj plus vzk. So means that this is the vx. So this is the vy. So this is the vz. Alright. So also, it can be simplified like this. So vx is equal to x dot. So this one dx over dt. So this one like this. So dx over dt. So it represent as the x dot. Alright. So this is the for vx. So similar for the vy. So vy here is y dot. Or you can write dy over dt. And then we have vz. So vz we have as a simplified we have z dot. So or dz over dt. So after you have determined vx, vy, vz, so you can determine the magnitude of the velocity of the vector as usual. Vx square plus Vy square plus Vz square. And then must remember that the directions of velocity is tangent to the part, this one. Okay, understand? Alright, next, the acceleration. So, the acceleration is the time derivative of the velocity or the second derivative for the position. So, if we have established what is the v, so you can derive. Okay, or you can double derivative of the position r. So, this is the for the acceleration. So now we have the acceleration in X, in Y, and also in Z. So how to determine the AX? So AX can be determined by the first derivative of Vx or second derivative of the X. Remember previous one? What is the X dot? X dot is the Vx. Right. So now we want to derive the to get the acceleration. So AX become what? So AX become this one, double dot for the single dot. Double derivative. Okay, understand? Okay, so as usual here we have AY. So AY, we have derive the VY here. Or you can have the Y double dot. Okay, and then the last one for AZ. So acceleration in Z. So acceleration in Z, you can derive VZ or you can double derive Z double dot. Right? You must remember the previous one. Okay, now after you determine the EX, AY and AZ, so you can determine what is the magnitude for the acceleration. This is for the acceleration. Alright, so you must remember the directions of the acceleration is usually not tangent to the path. So it is hodograph. Okay, understand? Right, so the applications of this rectangular method. So let's say we want to this figure say that the path of motion of a plane can be tracked with radar and is x, y, and z coordinate relative to the point of Earth recorded as a function of time. So how can we determine its velocity and acceleration of the plane at any instant? So we can resolve into position R, and then after we get the R, right, first we get the R. So R, you have xi plus yj plus zk, right? So after you get the R, then you can determine the V. After you get the V, then you can determine the A, right? So you have Vx square plus Vy square plus Vz square. And also for the acceleration, you have Ax square plus Ay square plus Az square. Okay. So next figure also, this is the roller coaster car travel down a fixed helical path at a constant speed. So how we can determine its velocity and acceleration? As usual, so you need to determine what is this R, right? So after you establish the R, then you can get what is the V and what is the A. Next, let's go through example 8.8. So the question given here, the box slide down the slope described by the equation y is equal to 0.05 x square meter. Okay, and x is in meter. So given by Vx is equal to negative 3 meter per second, and then given that Ax equal to negative 1.5 meter per second squared, at x is equal to 5 meter. So now we need to determine the y components of the velocity and the accelerations of the box at x is equal to 5 meter. So now we need to get what is the velocity and the acceleration at x equal to 5 meter. So this is the V, this is the A. So we have the component we have here in x and y. So this is the R, right? So now we need to get what is the V. So V, we understood that V is equal to Vx square plus Vy square. And then A also, A is equal to A x square plus AY square. So now to determine the velocity, so we need to determine what is the Vy, right? Because the Vx is given. And then for the acceleration also, Ax is given. So we need to get what is the Ay. So we have Y here. So we have the position Y here. So no problem. So you can find how to get. So now you have the Y. So you need to derive to get the velocity. And then you derive velocity to get the Ay. Understand? Okay. Next. So now we need to get what is the Vy, right? So Vy. So this is the Y. So Y is equal to 0.05 x squared. So we know that to get the Vy, we need to differentiate dy over dt. Right? dy over dt. So now, you derive 0.05 x squared. So it's become like this. So here you have, so here is also, this one is Vy. So Vy is equal to y dot, first derivative. So this is the first derivative. So you derive this one, so you get 2 times 0.05 and then x here. Right? So we can simplify. So we can get the 0.1x x dot here. So here we use the change rule because our position is with the time. So you use the change rule. So must remember how to use the change rule. So here we have determined the Vy. So Vy here is 0.1 x dot. So now you can get what is the Vy. So you can substitute. So you can substitute what is the x. So x is given. You already know what is the x dot and then what is the x from the equation. Okay. And then after we establish the Vy, then we need to get what is the Ay. So Ay here is double derivation. So double derivation of this one. So you can have, so this one, you derive this one 0.1 x dot here. So you can get this one. Okay. And then this one is the change rule. So you can have that x double dot here. So you must remember, you already know what is this. This one you know. And then this one also you know. So you can substitute, then you can get what is the Ay. Okay? Understand? Alright? Okay, next. So after we have the derivation, so this is the Vy. So Vy, so you can substitute what is the x and what is the x dot. So x dot is the what? Vx. Right. So you can substitute this one. Yes. So x is given by 5 meter and then x dot is given by -3. So your Vy is equal to -1.5 meter per second. And then next, what is the Ay? So Ay is equal to y double dot. So this is the equation that we have derived. And then we can substitute. So x dot is equal to Vx, right? So Vx, we have Vx square root. So this one you substitute. So this is the Ax. X double dot is the Ax. So you substitute, then you may get that this is the Ay, 0.15 meter per second square. Okay. So you can substitute into the equation to determine the magnitude for the velocity and also magnitude for the acceleration. Okay. So we go for the next example, 8.9. So this one, the particle travels along the path y is equal to 0.5 x square. When t is equal to 0, x equal to 0, y is equal to 0, and z is equal to 0. Okay, so that means that we have to sketch here. So this is our particle travel. So this is, let's say this is our particle, so this is our r, right? So we need to get what is the x here and what is the y here. Okay, so determine the particle distance and the magnitude of its acceleration when t is equal to y, when t is equal to 1, and Vx is given. So Vx is given by 5t, feet per second, where t is in a second. Okay, so now we need to get the particle distance. So what is the particle distance mean? So we know that this is the r, right? So we know that the r is equal to this one. This r is equal to this one, right? Y and x. Okay, so this y, this is x. So we need to get x square plus y square. Okay, so y we have here. So we need to get what is the x. So where we can get x? Where? From here. Right. From the Vx. Am I right? Why? Because we know that Vx is equal to dx over dt. So now we want to determine dx here. We want to determine the x. So what we should do? We should integrate, right? Alright. So now you know how to get the r, and then next we need to get what is the acceleration. So acceleration means that a is equal to ax square plus ay square. So now after we determine the ax and ay, so we can determine the acceleration. Okay, let's do that. So now we need to determine the, okay, so now we need to determine the x, right? So x component. So first case, we solve for the x component. So we have been given that Vx. So Vx is equal to 5 feet. So we understood that this one, x dot is dx over dt. Right. So now we need to integrate. So we need to integrate the Vx here. Okay, so we have Vx 5t. So we integrate 5t. So we can determine the x. So how to do that? So this one is become like this. 5 t square divided by 2. Right. So this one is become 2.5 t squared. So the limit here, so the limit is 0 to t. So now we have given t is equal to 1. So you substitute here t is equal to 1. So you can have that x 2.5. So this is the x, the position x. Okay, understand? Alright, so next we need to get what is the ax, right? Okay, so the ax. So ax, we can derive the velocity here, Vx here. So ax is equal to x double dot. So x double dot means that we second derive of the position here. So we have here this is v. So dv, we have 5t. So we derive 5t. So when we derive 5t, we get 5 feet. So 8x is equal to, when t is equal to 1, 8x is equal to 5t. So this is the ax. Okay. So next we need to get what is the y component. So y component, this is the y component. So y component, we have here, this is given by the question, y is equal to 0.5 x squared. So now, we already get what is the x here. X is 2.5. So you substitute here, 2.5. So you get y is 3.125 when t is equal to 1. So now we can calculate what is the velocity for Vy. So Vy, we derive this one. We derive 0.5x power of 2. So first derivation, so this is, we get the derivation. So 0.5 times 2 is 1, right? So we can simplify x dot single dot. So here you can substitute what is the x. X is a 2.5. And then x dot is what? X dot here is 5, right? So you can get 12.5 here. You substitute the value here. And then next, we determine what is the ay. So ay here, we second derivative of this velocity. So you derive this one. So you can get this one. And then you can substitute what is this value, this value, this one, and this one. So you substitute the value, then you get the 37.5. So this is the change rule, okay? Alright. Alright. So after you get each of the component, then we can substitute into the equation. So this is the position. So position x squared plus y squared. So you get the 4 feet. And then next, the acceleration. So the acceleration is ax squared plus ay squared. So you have to determine what is the ax, what is the ay. Then you can get the answer 37.8 feet per second squared. Understand? Alright. So that's all for today. Hope you can achieve the outcome number 3, which is to resolve the kinematic of particle by using the rectangular component x and y, x, y, z. Okay, see you for the next lecture. Bye.